Ladies and gentlemen, good morning and welcome to SK1. Today I would like to share with you some of the recent progress in meaningful type game theory, that's MFTG. So the idea in the next couple of minutes is to describe you a class of games with time delay, means the actions has a delay effect in the outcome of those games. First thing first, a couple of years ago, in 2006 and 2007, so the work are published in 2007, 4 papers on the evolutionary game dynamics, delayed game dynamics, in particular asymmetric delay, and we are one of the first group to introduce asymmetric time delay in evolutionary game dynamics. And here is the fact. As in many things in practice that you see, when you take an action, it takes a certain time period to put in place to have some effect, right? The consequences of those actions comes after a certain time delay. So we mimic that idea and we incorporate this into games. So you take an action now, for example, you start a business now and you have to work hard, and after some time delay you see the output of your business. You get exposed to a virus on the street, and 2, 3, 4, 5 days later you see the effect of that exposure to the virus, right? So you will see really if you are really sick now or after five days or not. It's not that instantaneous for many of the cases. So that's similar for many other examples. So here is the setup. We consider a certain number of agents, let's say finite, for the sake of this presentation. So we have a finite number of agents. Each of the agents has let's say few choices, finite number of choices. So for agent I as an action AI that belongs to a certain finite set, and agent I has also time delay associated to each of those action AI, right? So let's denote the time delay by tau, and the tau I is going to be a vector for agent I, and the tau I1, tau I2, tau I3, tau I number of choices of agent I. And we do that for all the agents. And if agent I chooses, for example, AI, and all the agents have made that choice, that will be an action profile A, and A has an effect in the outcome. That's classical, the utility function. And if you go beyond the standard utility function, you might consider non-von Neumann utility functions or Minfeld type utility function, and in that case you get a function of AI and a function of a distribution of A in this case, right? So now this outcome will have observation realized after a certain time delay. For agent I it will be tau I associated to action AI, right? So we build this together and then we make a game dynamics. So what we found is the following. So in the 2007 papers, 4 papers are published in that area, and a couple of them have been published years later because of the review delays and so on, but fully published by 2011 or 2014. So for the latest ones, and the extensions to meaningful type game dynamics more recently. So here is the preliminary results. The first preliminary was of course symmetric delays were in the literature. Symmetric game dynamics were already analyzed, but the asymmetric game delay was the target at the introduction in the game dynamics, because the games are not symmetric. So there was no reason that the delays to be symmetric, although it might happen in some specific scenarios. So here is the outcome. You consider a game dynamics, a game, classical game, and you analyze your outcomes, and then you look at game dynamics, and you try to find the equilibrium outcomes through dynamics or through learning process, and you look at the outcomes. If they were converging, for example, to one equilibrium, let's say to one of them, there might be have multiple. To one of them, if there is a convergence to that, if there any, you might say that okay, this is a stable equilibrium according to that dynamics. Now, if you incorporate a time delay in that, discrete or continuous, that's discrete and continuous time doesn't matter. If you incorporate a time delay in that, actually the conclusions might be different. So typically, evolutionary stable strategies might be unstable and because of the delay. And for some of the dynamics, it doesn't matter. Whenever the time delay is non-zero, the equilibrium becomes unstable. For some other dynamics, unfortunately, when the delays are small enough, then you have similar conclusions, and the people try to find the ranges under which is stable, unstable, and the transitory phases, oscillatory phases, and so on. So this is very interesting area, very exciting area, and it's closer to the practice because where you see that things are moving, they are changing, and it's not like you go to a steady state and game over, right? So that's what we wanted to share with you today. I would like to thank you for your attention. Thanks for your time, and see you soon on SK1. Bye.